Just we did the whole thing that when you have a heterogeneous catalyst, what happens is that the catalyst is going to have a different state compared to the reactants, which is why what's going to happen is that adsorption is going to happen. We discussed that transition metal ions have very high charge density, which is why if a molecule comes close to a catalyst, like a transition metal catalyst, its electrons, they get attracted to the transition metal. Transition metals, they lose their tendency to lose electrons. Instead, they develop this very weak attractive force for electrons. They don't attract those electrons very strongly. So in that way, the bond between the atoms is going to break. And that's adsorption. And then you have deadsorption, which happens that what happens then is that when the atoms, they fly away because they have some kinetic energy, the bonds are broken, the weak bonds are also going to break. So the weak bonds between the catalyst and the reactants would also break. So we did all of this. We did talk about them behaving as good catalysts. Why were they good catalysts? Because of the greater number of protons in transition metals, they're smaller ions, which is why they have greater density, charge density, which is why they have this weak attraction for electrons. And unlike non-metals, they don't attract the electrons that strongly. They don't gain those electrons, which is why deadsorption is possible. So this was an example of heterogeneous catalyst, and I'll just quickly. So we did the Haber process, and palladium and platinum and rhodium in the catalytic removal of oxides of nitrogen from the exhaust gases of car engines. I'll just do that quickly. It's the same exact adsorption, deadsorption thing. So I'll just add a point to this, which is that other examples. So otherwise, you're going to explain the whole adsorption, deadsorption thing. So the other examples are platinum, rhodium, or palladium in catalytic removal. Although you have a lot more examples than that, any example where the catalyst has a different state, that would be heterogeneous catalyst, like hydrogenation, etc. In catalytic removal of oxides of nitrogen. As a first thing, I'll just go over this. What happens in this reaction, that you have car exhaust gives off many different, it gives off many different types of oxides, which are known as or classified as pollutants. Some of those oxides are carbon oxides, monoxides specifically, oxides of nitrogen like NO or NO2. And it also has unburned hydrocarbons like CXHY, whatever the hydrocarbon is. When the reaction happens, what the catalyst does is that carbon monoxide turns into carbon dioxide. The oxides of nitrogen, they turn back into N2. And the unburned hydrocarbons, they get oxidized as well into carbon dioxide and water. So you don't have to explain much. It's exactly the same thing. Adsorption, deadsorption. The platinum, rhodium, or palladium in the car exhaust, the catalytic converter is in the car exhaust. So whether it's platinum or palladium or rhodium, you kind of have the same thing. The reaction molecules are going to bond with it, and they're going to get adsorbed, and then they're going to get deadsorbed. So it's the same adsorption. The old bonds are going to get broken, and the new bonds are going to be formed. Okay, so it's the same thing as discussed above. Okay, is this clear? Sam, is this clear? Bazga, Roha, is this clear?
Yes, sir.
Yes, sir.
So we're going to move to the next one. The next one he's talking about is first one, homogeneous catalyst. So two examples of homogeneous catalyst we're going to do. The first one is the very first one, homogeneous catalyst. Homogeneous catalyst is that the catalyst and the reactants are going to have the same phase. So catalyst, reactants have same. They've got the same phase. Now when we so either we'll do example one first, which is, now remember these examples are given in the syllabus, so you have to be very specific. You have to remember all of these examples, like the atmospheric oxidation of I mean, this is about acid rain, the atmospheric oxides of nitrogen, the oxidation of atmospheric sulfur dioxide. So we'll just do a brief background first. What happens is that you have flue gases. Now flue gases, and I think there's an E. So flue gases. Flue gases are sulfur oxides and oxides of nitrogen, like NO or NO2. I mean, these are some of your most common pollutants. Where do you get those pollutants? The way you get these pollutants is oxides of sulfur are produced during combustion of fossil fuels, especially the raw ones like coal. In thermal power plants, combustion of fossil fuels, they've got a lot of sulfur in them. So that's number one. And number two is volcanic activity. So most of the fire that happens or the heat that is being produced, it's burning the sulfur that's in those volcanoes, and you're getting the same reaction in all two cases, that sulfur oxides are produced. So SO2 is, you get SO2. Now, where do you get oxides of nitrogen? The way you get oxides of nitrogen is it's either lightning strikes or it's car engines. In both cases, what happens is that air heats up and burns. So air burns up, air has nitrogen, and it ends up at high temperatures, it ends up reacting with the oxygen in the air to form into NO2 or NO. I said then in the atmosphere, this is the reaction that takes place. Sulfur dioxide, so this is the main reaction that takes place where NO2 is acting as the homogeneous catalyst. So here's the reaction. You've got SO2. I say it reacts with NO2. NO2 first oxidizes SO2 to SO3. And NO gets reduced. And then NO gets oxidized back to NO2 in the atmosphere. So that is an example of a homogeneous catalyst, where NO2, you start off with NO2 and you get NO2 back again. So it's acting as an homogeneous catalyst. You can, now for this one, you don't have to know the reasons why this is happening. Just the main idea, this is an example, and NO2 is behaving as a catalyst. So NO2 remains, because there is no transition metal involved in this one, it remains unchanged. And NO2 first oxidizes. So NO2 is a good oxidizing agent. Oxidizes SO2, and then in the next step, NO gets oxidized back to NO2. So you've been studying this reaction since O levels. So hopefully this one is clear. There's no other, you don't have to go into a lot of detail with this one. Is this example clear for homogeneous catalyst, that the reactants and the catalyst are in the same state? NO2 is the catalyst in this case, if I haven't written that. You clear at this one?
Yes, sir.
I said, now the other one, this one, iron and the I-1S2O8 reaction, right? I mean, this specific one. Now this one, you got to go into a bit more detail, and this involves a bit of electrochemistry as well. So first thing, and this one involves a transition metal. So the thing is, again, it's an example of homogeneous catalyst. So he's talking about how do Fe2 plus or Fe3 plus, remember both of them can act as catalysts, in the I-1S2O8 2- reaction. So what's happening there? So we need to figure that one out. Now, the first thing about this is, we did discuss this, that somewhere above, we discussed this thing. Then I told you that the elements that are on the left side of the periodic table, they really like to lose electrons. So these ones, they really like to lose electrons. The elements that are on the right side, sorry, on the left side, on the right side, they really like to gain electrons. So transition metals are kind of in the middle. They don't, they lose their tendency to actually lose electrons, and they have this very small tendency to attract electrons. So they're somewhere in the middle. They can do both things. So the thing with transition metals is, they can lose electrons. So if it comes to Fe losing electrons, it can lose electrons. And when it comes to Fe2 plus gaining electrons, it can also gain electrons back. So they tend to kind of do both things. Okay? I mean, if you talk about potassium, it's always going to lose electrons. It's always going to try and form a potassium plus 1 ion. That's it. I mean, it doesn't want to go back. It always wants to lose electrons. If you talk about bromine, it's always trying to gain electrons. Transition metals are kind of in the middle because of their proton numbers. You keep on moving to the right, the number of protons keep on increasing. So these ones, they can turn into an ion. They can turn back from an ion to the original metal back again. I mean, for example, if you take silver, I mean, silver can lose electrons to form, I mean, it would be losing electrons with a bit of difficulty, but at the same time, it can do the opposite as well. Silver plus 1 can gain those electrons back to form silver again. So that's the thing with transition metal ions when they act as catalysts, that they have, I mean, they like to lose it. I mean, they don't really like to lose or gain electrons, but they can do both. So they can lose electrons or they can gain electrons. They're kind of in the middle. TK, is this point clear? Sam, is this clear? Zohab, Bhaskar, Minail, is this clear?
Yes, sir.
So this is something that happens over here as well. Now, to proceed further, the first thing is I'm going to try and let's figure out what the reaction is. We're going to bring in the catalyst later on. Now, one thing that you have to remember when you're dealing with this is, okay, let me open a data booklet. So when you're dealing with this, there would be, you have to know what electrochemistry is all about. So in the data booklet, which would now be actually given as part of the question, all this information, you're given all these reactions. So I'm not going to go into a lot of detail at the moment, but I'm going to explain these values. These are your potential values. So here's if you have a higher potential, the rule is a high E naught indicates, this is the voltage on the cell. A higher voltage indicates, the basic idea is a higher voltage indicates that it likes to gain electrons. Okay, so whenever you have a higher voltage, it likes to gain electrons. For example, if you see over here, silver over here, it likes to gain electrons, and gain of electrons happens in the forward direction. Remember, these are reversible reactions. So this is a table that we will use to predict redox reactions. So these are reversible reactions, but if the potential is really high, that means they like to really, really gain electrons. So silver ions really like to gain electrons and form silver. Silver doesn't want to do the opposite. Silver doesn't like to lose electrons. It doesn't like to form Ag+1 ions. That's the whole idea. Or vice versa. Vice versa is, if you have a lower E naught, then the substance really likes to lose electrons. And it's a relative comparison. So for example, if you look over here, here's calcium. Calcium is very reactive. It's got a voltage of minus 2.87. So that means calcium really likes to lose electrons. So based on this table, we're going to predict whether the substance likes to gain electrons or whether it likes to lose electrons. So you've got all these, you can predict a few of them, like sodium. Sodium really likes to lose electrons. So look at sodium. Sodium is minus 2.71 volts. That means sodium really likes to lose electrons. So that's the whole idea. That based on this table, you will be able to figure out who wants to gain electrons and who wants to lose electrons. And remember, it's going to be a relative comparison. You'll be comparing reactions. So these are half equations given. So if we go back to our question, you've got I-1, and you want to figure out a reaction with S2O8 2-. So remember the whole thing, higher potential gains electrons, lower potential loses electrons. So I don't know which one is going to gain electrons, which one is going to lose electrons. At the moment, I have absolutely no idea. So what I'm going to do is I'm going to open the, where did my, it's over here. So I'm going to open the data booklet and I'm going to find I-1. So I-1 is right in front of me. So here's I-1. And it has a value of 0.54 volts. So I'm going to take that and I'm just going to copy this. So the equation that was given, I'm just going to copy the reversible reaction, I2 plus 2 electrons, reversible 2I-1. And the E naught that's given is 0.54 volts. So I found an I-1 reaction, but I don't know at the moment what it's going to do. Everything would be decided by the potential, what it likes to do. The next one is S2O8. Find S2O8. So if you look carefully, there's S2O8 over here. So here's your reaction. It's S2O8 and the potential is 2.01 volts. So I'm going to copy this equation as it is. So I've got S2O8 2-. It gains 2 electrons and it's in equilibrium with 2SO4 -2. And the E naught for this particular reaction is given as 2.01 0.01 volts. Now, we're trying to figure out of the two, who likes to gain electrons, who likes to lose electrons. Now, the rule is electrochemistry, not all substances. Sometimes substances want to gain, some substances want to lose. So the rule is high E naught likes to gain electrons. And the one that has a lower potential, it likes to lose electrons. So out of the two potentials, this one is the higher potential. Remember, it's a relative comparison. This one is the higher potential. So that means it really likes to gain electrons, and the other one has a lower potential. So that indicates that it really likes to lose electrons. So higher gains electrons, and the lower one loses electrons. I mean, is this clear up till this point?
Yes, sir.
Okay, बाकियों को Zoha, is this clear? Sam, is this clear?
Yes, sir.
Yes, sir.
Asha, so remember, this is part of electrochemistry, so I'm not going to go into a lot of detail about this, but I'll just talk about this thing that why do we say higher potential gains electrons? Because the reason the cell has a positive charge is that the reaction has consumed all the electrons. So the electrode becomes positively charged because whatever this reaction is, it has consumed all the electrons. So it has gone in the forward direction. The reason why some of them have lower potential or negative potential is that the reaction is producing a lot of electrons, which is why your electrode becomes negatively charged. So this is how we figure out who wants to gain electrons, who wants to lose electrons. So if we go back and we construct the equation, the overall equation can be constructed by using these two reactions. Now we have figured out who does what. So I can figure out the overall reaction now because I know my reactants and I know my products. So my reactants are these. It's I minus 1 trying to lose electrons, so it's 2I minus 1. I'm going to add up the reactants. The other reactant is this one. So I've got two reactions, two things going on. I minus 1 losing electrons, S2O8 gaining electrons. So it's 2I minus 1 reacting with S2O8. These are my two reactants. And my products that are being formed are, in the first case, the product that is formed is I2. In the second case, the product that is formed is 2SO4. 2SO4 minus 2. So I've actually figured out my reaction now. I figured out who lost electrons, who gained electrons, and I've combined the two things together. I've combined the oxidation equation, which is the first one, I think, oxidation, with my reduction equation, which is the second one. So I've got a redox reaction now. TK, and over here, just don't get confused. I've just added up the reactants. This is the reactant. This is the reactant in the second one. And I've added the products. The products are in the first one and the second one. The electrons lost and gain are equal, so I don't have to do anything in that case. So this is my overall reaction that happens when I react 2I minus 1 with S2O8. So this is my overall reaction, right? And the electrode values are telling me that it's a very feasible reaction. It's a very feasible reaction. Because we predicted this reaction using the values over here. There's another thing in electrochemistry that is known as the E naught cell. The E naught cell is the potential difference. A potential difference determines how fast the electrons would flow. Like if a battery has a very high potential difference, that means electrons would flow very energetically in the circuit. So this one has a potential of 2.01, the other one has 0.54. So the potential difference between the two reactions is really high. That means it's going to be a vigorous reaction. It's going to be a very fast reactions, and electrons would flow very quickly. This would lose electrons, and those electrons would travel to the other one, and they would gain electrons. So that's, if you subtract the two things, that gives you 1.47 volts. So theoretically speaking, it's a very feasible and should be a very fast reaction. But this reaction does not happen. So practically speaking, I mean, theoretically speaking, we said that it's a pretty fast reaction. But practically speaking, no reaction. You almost get no reaction. It's got very high activation energy. So our calculations stated that the reaction should have been very fast. But the reality is kind of different. Okay. Is this clear so far? Yes or no? Is this clear?
Clear.
Yes, sir.
We haven't discussed why the reaction is not happening, but hopefully the first part, like the reaction according to the electrochemistry rules, must or should have been really fast. So just 1 second. I've lost my pen. Just a second. So now, can anyone guess what's wrong with this reaction? Why is this not happening? Even though mathematically speaking, it's a very feasible reaction. Can anyone guess what's wrong with this reaction? I mean, look at the equation. Just use your common sense. It's look at these two reactants and tell me why would a reaction involving these two ions would be very difficult. Any wild guesses? Nee, Basga, any idea? Zoha, Minahil, Sam, any idea? Just a second. So, TK Zoha, that's right. So the thing is, that is exactly right. So the thing is that if you look at these two ions, both of them are negatively charged. And we know that negatively charged ions repel each other. So the reason it's got very high activation energy is because the ions are never going to meet each other in the first place, even though the reaction is very feasible. So negative ions, they repel each other. So even if you add them in the same solution, they'll spend all their time avoiding each other. They're not going to interact with each other. So very large, I mean, you have to really give them large kinetic energy is needed just to make them collide. So that they collide. So SO4 minus 2 and I minus 1 are never going to come even close to each other. So they're going to keep so really hard for them to actually combine or collide in any way. Okay. Sam, is this clear?
Yes, sir.
अच्छा अब इससे आगे ये कि so now we know that this reaction is not going to happen. So now we're going to bring in a catalyst. And the catalyst is, so I'm just going to copy these two. So now I know that all our working that we did, this oxidation reduction thing, is not really going to happen. So as a all of this, I mean, our goal is for it to happen. But in reality, in all practicality, it's not going to happen. So that means this is not going to lose electrons. This is not going to gain electrons. Reduction will not happen. Oxidation will not happen. Even though it's higher, the other one is lower, but there won't be any reaction. So now to make the reaction possible, I'm going to bring in the catalyst. Now, the first thing, remember, these two equations are not going to interact with each other. So I'm going to keep them as far away from each other as possible. So we can safely say that even though the reaction is feasible, these two are not going to interact with each other. They're not even going to meet each other. Now I'm going to bring in the catalyst. Remember, I talked about transition metals that they can gain electrons. They can also lose electrons. So they're kind of in the middle. So in the data booklet, you're given this equation, this reaction. This has an E naught of 0.77 volts. So I've added this. So I've added this catalyst now. So I've added this catalyst now. Now, the black equations, the black ones, I minus 1 will not interact with S2A2 minus. So they're not going to react with each other. So what happens is that the catalyst goes and starts reacting with both of them. I mean, this equation also interacts with this one, and it also interacts with, so the iron ions are basically reacting with both of them. In the first one, let's focus on the first one. I said the first one, what happens is that, I mean, these two, they're going to interact. The iron is the higher potential, so it gains electrons, and the other one has the lower potential, it loses electrons. Just to make the number of electrons gained and lost equal, I'm going to multiply this entire equation by 2 so that I don't have a problem balancing the equation. So the first one is, what are my reactants? It's 2i minus 1. It reacts with, reactants, add up the reactants. So this is one of the reactants. 2Fe3 plus, that's your other reactant. And what are my products? The products are, the product in the first one is I2 getting formed. In the second one, it's 2Fe2 plus that's getting formed. So I2 plus 2Fe2 plus. So that's the first reaction that's going to happen. Then what's going to happen is that the same iron ions are going to go and react with the, these SO4, S2, S2O8 ions. Now in that case, this has the higher potential, so it gains electrons. The other one has a lower potential, so it loses electrons. So if you compare, look at the green box, higher potential, lower potential. So it gains electrons, the other one loses electrons, and we can sum up their equation. And their equation would be that the reactant is S2A2 minus. And it reacts with the other reactant over here is 2Fe2 plus. And the product that we have is, in the first reaction, in this reaction, the product is SO4 minus 2. In this other one, it's Fe3 plus. So it's 2SO4 minus 2, and the other one is 2Fe plus 3. So ये सारा आपके पास आ गया, ठीक है? So you got these two reactions. So understand this point first. I'm just going to repeat the point. This and this were not reacting with each other. And the reason we discussed that the equation that they were making, they were both negatively charged ions. So they're going to be as far away from each other as possible. So practically it's impossible to bring them together. So they're not going to react with each other. So we're going to give up on those two equations. I mean, this will not react with this one, even though it is feasible. I brought in the iron ions, and what happened is that in the red box, the iron ions reacted with the iodine. I mean, this first equation, I minus 1 is the lower potential. It lost electrons. Fe3 plus had the higher potential. It gained electrons, and we came up with this equation. In the second one, the same iron ions, they ended up reacting with S2O8. This being the higher potential gained electrons, this being the lower potential ended up losing electrons, and we came up with these two equations. Now, if you focus on these two equations, you'll notice that the iron ions are acting as a catalyst. Why? Because they remain completely unchanged. You started off with Fe3 plus, and you end up with Fe3 plus back again in the second step. So that means the Fe3 plus remains unchanged. The reactions could have the other order as well. So Fe3 plus remains unchanged and the reaction speeds up. As the first thing, it is exactly the same reaction because the products are iodine and SO4 minus 2 in 2 steps. The products in the reaction that we had given up on were the same, I2 and SO4 minus 2. So you're getting the exact same products, but in 2 different steps. In the first one, you're getting iodine. In the second one, you're getting SO4 minus 2. The iron ions completely remain unchanged. Now so is this clear? First thing, is this clear?
Yeah.
Yes,
So now the very last thing is, why is the reaction? Why are these 2 reactions faster? What's the reason for that? Kya hoga? Why is it faster?
Because of the catalyst.
It is because of the catalyst, but how is the catalyst speeding them up? I mean, it's the same reason why the first reaction wasn't happening. Like, what are the charges on the ions now? They're opposite, right?
Oh, the charge changes.
And these 2, the ions are now oppositely charged. That means even if they're very far away from each other, they're going to attract each other and they're going to interact with each other and they're going to react. The problem with the first reaction was that both the ions or charges were negatively charged, right? So they were never going to meet each other. They were never going to interact with each other. So now you have, so the reason the reaction speeds up now is that they're oppositely charged. So you don't have to give them a lot of force so that they collide with each other. They're going to collide with each other or attract each other anyways, whether you heat them up, whether you give them kinetic energy or not. So reaction speeds up. Why? Because oppositely charged ions, they attract. And you're also getting the same product. You clear this, Sarang? Is this clear?
yes, sir.
Okay.
Yes, sir.
So you have to remember this specific example very carefully. And remember, this can only happen with a transition metal because transition metal can do both things. It can, with some elements, it can gain electrons. With other elements, it can lose electrons. A group 1 metal will not be able to do that. It would always lose electrons. And a group 7 non-metal would always gain electrons. It's not going to do the opposite. So transition metals can actually kind of do both things. Let's continue with this tomorrow now. We're running out of time. We're done with heterogeneous catalyst. That was the other example that we want. Sorry, homogeneous. This was the other example we had to do. But you have to remember the whole example specifically. Not the general things, the whole thing. Let's continue tomorrow then. Okay, everyone. Take care, Allah Hafiz.
Bye-bye.